Yeah, thank you. Thank you for the introduction, Devara. And thank you for having me here. And thanks to everyone for coming to my talk. So today, I would like to talk to you about this local to global approach we developed for designing policies for decision-making problems in large stochastic networks. So this talk is based on a sequence of papers we wrote during the past 2 or 3 years, mainly led by my PhD student, Ige, at CMU, and in collaboration with Xiang Chen, who is like an undergraduate student from Tsinghua, and our collaborators Xiaomi and Yudong from UW Medicine. Okay, so I'm quite excited about what we were able to achieve through this framework. So we were able to design policies that are different from the traditional class of policies, and which leads to the removal of a long-standing barrier. And also our approach is quite generalizable. It can handle a strong heterogeneity in the system, which is usually a challenge for traditional methods. Okay, so let me get started. Feel free to ask questions anytime. And if you don't ask questions, I may ask you questions instead. Okay, so be prepared. Okay, so large stochastic networks or large stochastic systems, they arise from a lot of applications in practice. So because we are living in this era of unprecedented scale, everything is large scale. For example, if you think about communication systems, it's larger than ever because of the increasing number of smart devices, personal devices, and so on. And modern computing systems are massive because they need to support the staggering need from computation, especially in AI and machine learning applications. And almost everyone is on a social network, and also service platforms like ride-sharing systems provide a lot of service. Like for example, I think for the ride-sharing service in Boston, every day they provide more than 100,000 rides. Okay, so all of those are pretty large systems, and the scale makes it tricky to understand the dynamics in those systems and design policies for decision making in those systems. However, fortunately, most of those practical problems are not that adversarial. They usually have a certain structure that can help break the curse of dimensionality. So for example, low-rank structures are explored a lot, or sometimes when you model those as a queuing problem with many queues, there are state aggregation, so you can use techniques like mean field analysis or diffusion approximation and so on. Okay, so in our work, we would like to advocate this perspective that you should make use of the independence structure in those systems. So this is like a common idea that shows up in many problems, many approaches, many areas. But we just found it the following view very informative, and it forms the basis of our approach. So basically, it's a very simple principle. If you have a system that has n components, but if they were totally, completely independent, then you can just separate them, and then it becomes n separate problems. You can solve them individually, and you are not subject to any complexity, exponential n or anything. Okay. Of course, all those problems, things are not completely independent, but still there's a certain independence going on, which still allows the decomposition in some form. Okay, so let me give you some examples about this independence structure. So the first example comes from scheduling for computing systems. So you have a lot of servers, and nowadays the jobs come in, and each job, you can think of it as a virtual machine, or it's called a container job. So basically, it requires a certain amount of resources, from different types. So for simplicity, I'm just illustrating maybe one-dimensional requirement. You can think of it as the number of CPU cores, for example. And then you look at all the servers, you decide where you want to schedule this job. Okay, so for this problem, and the servers has this capacity, and jobs have resource requirement, and then you need to be subject to the resource capacity constraint. So for this problem, it has like each component here is a server, and it has many servers. So for each component, the state is like the kind of jobs it's running. So like the resource usage from different jobs, okay? And this state could change, right? Like the user who submits this job could change the way they use this like virtual machine. Like maybe they go from like intensive usage to like lower intensive like usage, so the state could change, okay? And then like if you think about the state transitions here, if you know the states of all the servers and before the next job comes in, then the transitions from different servers are independent because like the jobs like running on one server, their behavior is determined by the users, and they are kind of just separate from the jobs on another server. Okay, so then like the transitions here are independent from each other. Okay, is that like reasonable? Like, okay, you look like you have a question.
There's coupling happening in terms of how job allocation is done.
Yes, yes.
And then there is a sort of servicing of each of the queue that's happening.
So yeah, so here there's no queue. It's just like the job, like you hosted the job on the server.
The job disappear or job remain there?
Job could disappear. The job could remain there and change like maybe at this moment I need one CPU core, but the next moment I need 2 CPU cores. It could change state.
What do you want us to agree right now on this slide?
The transitions, given the job states before the next arrival happening, are independent from each other across servers. That's what I'm trying to convey.
And there is it's basically you're saying that's a physics.
Yeah, that's physics. Yeah, that's just because they are separate. Yeah, yeah, it's reason to model it that way. Yeah, okay. Okay, cool. So let's look at the next example that comes from this ride-sharing application. So here you can think of each car as a component, and then like if you look at the state, it's basically where it is right now, and whether it's serving like a customer or not, and where this customer is going. Okay, so then like given their current states before like you make any other like decisions, then each car's behavior is kind of independent from another car, right? They just go on their different route and assume there's like no strong conjunction or anything. So it's reasonable to assume they are independent from each other.
And with the assumption that they are not the primary reasons why conditions are happening in the system.
Yes, yeah, let's assume that, yeah.
So maybe one way to think about where this would break down would be if I think of the state as also capturing the location of different drivers. And I incentivize some drivers to be positioned somewhere else, but other drivers I don't incentivize to. And then that no longer.
That actually doesn't break this because like I'm deliberately saying the transitions are independent given their current state and before or like given the decisions you've already made. Like you can't look at all the cars and decide, okay, yeah. So in that way, yeah. So in that way, you can see that like their states evolutions are definitely not independent because whenever you make a decision, you look at all the car states ideally, and then like you make the decision. So that like couples the state dynamics together. But the only thing I'm pointing out here is like the transitions are independent from each other given the state, given the current decisions. Okay. Okay. So I'll make this more precise, but this is like a high level, like where the independence could arise. And then like based on this kind of independence, this like a partial independence structure, we were able to like think about, like come up with this approach that we call local to global. So here is just a high-level description of it. So our goal is to design a decision-making policy that like optimizes certain performance. And then like it basically has 3 steps. First, we want to decompose the system. And we cannot decompose the original version of the system because like it's not totally independent. But we may come up with some average version of it that's decomposable. Okay? Then like next one is like after we decompose it, we have separate problems. We solve each one. We have like an individual policy. And then like in the last step, we try to piece together all those policies to form a valid policy for the overall problem with the performance guarantee, okay? So it's very abstract right now, but I'm going to go through some concrete problems, okay? Okay, so yeah, this is just like a list of the problems we have worked out using this approach. First one is this like bin packing problem, like I described in earlier slide. And with this approach, we were able to capture the resource like usage fluctuation through across time. And this was like a main reason for a low utilization of scheduling in some of the computing systems. And we were able to capture that and work out like a asymptotically optimal policy that maximizes utilization of servers. And then like we have this sequence of work on the so-called restless bandit problem. And this is one I'm going to focus on in the next part, okay? And then like there's a generalization of the restless bandit problem. It's called the weakly coupled MDP. And I'm going to also briefly mention this. So I'm going to focus on this, and I'm going to briefly mention this, okay? Okay, so maybe, yeah, now let me get into this restless bandit problem, and things will become more concrete, okay? So this is a very classical problem. And, but first, a little bit of disclaimer here, because many people are more familiar with the stochastic multi-arm bandit problem. So in this problem, you have n arms. Each arm doesn't have any state or anything. It's just you pull it, it gives you a reward coming from an unknown reward distribution. And then your goal is to try to kind of try different rewards, learn their expected reward, try different arms, learn their expected reward, and try to pull the best arm as much as possible. So for this problem, it's more like a learning problem. There's this trade-off between exploration and exploitation, okay? So the restless bandit problem is a little bit different. There's some connection, but I'm not going into that. So it's also called the Markovian multi-armed bandit problem. So for each arm here, it has a state. And when you pull it, it will have a state transition following certain transition probabilities. And if you don't pull it, it can still transit and following maybe a different set of probability distributions. Okay, and we assume, so the state could be something like, I'm just using numbers to indicate the state, and we assume that we know like the transition kernels and the reward parameters. Oh, by the way, each arm generates a reward depending on its current state and whether you pull it or not, okay? And then your goal is still to like try to maximize reward, but under known like problem parameters. So this is at least like, oh, another difference is like you can usually pull a fraction of the arms rather than just one arm, okay? So let's say like alpha is a fraction, okay? So for this problem, at least so far, it is a planning algorithm, like a planning problem, or like a computational problem. You are given all the parameters, so you're just trying to compute like a policy, near optimal policy.
Like here, unlike there, where it's a reward is you keep pulling the same arm over and over again, ideally if you figure it out.
Yeah.
Here, sort of depending on what you pull, transition would happen, and that transition would lead to different future reward. So now you're worried about immediate reward or some kind of a discounted.
Yeah, right. So yeah, I'm going to make it clearer, okay? We are actually going to use the average reward criteria, okay? Yeah, but right, like this is the thing you're trying to figure out, okay? Okay, so yeah, so for this problem, like I said, like, oh yeah, let me make it more precise. So for each arm, you can think of each arm itself as a Markov decision process. It has a state space, which let's assume is finite. And then like the action space is binary because you either pull it or not pull it, okay? So the active means pulling, passive means not pulling. And then we have like two sets of transition probabilities based on the action, okay? It's called restless because even if you don't pull it, it could still have like state transitions. Okay, and then there's a reward function of state and action, and then like our goal is to maximize the long-term average total reward from all the arms. Okay.
So for all the arms, it's the same transition problem.
Yeah, yeah. Thank you. Yeah, right now they all have share the same set of parameters. Okay, it's a homogeneous arm problem. Okay, yeah.
Does the theory depend on like the decoupling of the Markov kernels? So like if your state depends on the state of the other arms, does that affect things?
Oh yeah, sorry, I forgot to mention, like the state transitions are independent across different arms. So given the current state and the current action, the state transitions are independent. Yeah, okay. But when you make this decision, you would look at like all the arm states. Your policy is basically mapping that comes from, that maps like a joint state of all the arms to like which arms you want to pull, okay?
Yeah, how do you initialize the states?
It doesn't matter much here, like
It's a stochastic kind of distribution, right? You initialize, or is the fixed stuff?
it does, yeah, it could, either way, it doesn't matter that much.
How many policies do you consider stochastic in the policy?
So theoretically speaking, you could have, like if you just think about the set of Markovian policies, it could contain the optimal policy, Markovian and the stationary policy. But we will see that like what our policy looks like. Okay.
So effectively, you got n independent at some level MDPs, and then sort of thing that couples here is what fraction of things that you can activate at any given point.
Yes,
in time.
exactly.
And you want to make that as a function of sort of depending on what state space is.
Right. Yeah, I'm going to give an example here, okay? So to make this more concrete for everybody, okay? So, oh yeah, alpha n is called the budget. Okay, so I'm going to give a concrete example, okay, for everybody to think about. So for this problem, for every arm, it has like 8 states, okay? So if you are a professor, you can think of each arm as one of your PhD students, okay? And if you're a student, just pretend you are the professor and think about all your students, okay? And this 0 to 7, like they are like their academic maturity or something, okay? And then like your job is to move students from 0 to 7, basically. And then like if they go to 7, then like they can graduate, and that's when you get a reward. And then like you hire a new student, you start over, okay? So that's the only time you are going to receive a reward, okay? So this is just how the example is. And then like, let's see how your action could affect that. So your action could be, like the active action is like, I'm going to meet with this student today, okay? The passive one is like, I'm not going to meet with them. Okay, so then like, so the students are like, you can think of those students with the levels 0, 1, 2, 3 as more junior students. So for them, if you meet with them, they tend to like go to the right, they tend to progress, okay? If you don't meet with them, they tend to like go back, okay? However, if you look at the senior students, the senior students have like very, very different mindset. If you dare to meet with them, they are going to go back, okay? They don't want like meetings, okay? So, and if you leave them alone, they make good progress and then like they kind of just graduate, okay? And then like the problem you're facing every day is like, I have those students, they are in those days, who I should meet with today, okay? Suppose you can pick for 4 out of 8, okay? So then like there are many reasonable like answers. Like, does anyone want to try to see like what would be a reasonable answer here just for this given state? Like, who do you want to pick to meet with today? I do have 3 options for you actually. So
0 and 3 ones, yeah?
Which ones did you pick?
0 and 3 ones.
0, yeah, like that's a reasonable answer A, okay? Yeah, that makes sense, right? Like it seems like junior students want more meetings. And there's another answer which is like this, okay? Which
Maybe it's really better.
Yeah.
0 cannot go on the left.
Yeah, 0 cannot get worse, so you may want to prioritize 1 and 2, okay? And then there's another answer that looks like this, which is a little bit hard to see where it comes from, okay? But it actually comes from our policy, okay? Okay, so we'll see like which one makes more sense later on. Of course, like what you decide to do like at one moment doesn't matter that much. What matters more is your policy, right? Okay, okay, so yeah, so this is like the example you can keep in your head. And then like, for this problem, if you think about all the n arms together, they form like a giant MDP. The state space is the joint state of all the arms. And yeah, so the action space is like also like alpha n out of n ones, okay? So if you write it out, just a little bit of notation here. This is like basically you want to find the policy pi. This is the state of arm I at time t under policy pi, and this is the action you take, and this is the reward. And then you sum over all the rewards from all the arms, and then you normalize it by n. So we are looking at reward per arm. Okay, and then this is the time average notion. So we are looking at the average reward problem here. Okay, and the constraint is every moment of time you can only pull alpha n of them. Okay. Okay, so hopefully this makes it like the setting really clear. Okay, and then like this problem, if you just solve it like straightforwardly, then it's going to be pretty complicated because of the size of the state space and the action space. So what we are going for is this refined goal here, where we want to efficiently compute a policy that is asymptotically optimal. So here, like Rn star is the optimal reward when you have n arms. Rn pi is like the reward under your policy. We want the gap to go to 0 as you have more and more arms. Okay, so this gap here is called the optimality gap. Okay, so is the goal clear to everyone? Okay, cool. So then, like, let's review some of the existing approaches, and those approaches are mainly based on index policies or priority policies, which makes intuitive sense. So what they do is like basically you assign the states of priority order. And this might be implicitly what you were thinking when you look at the problem. So for example, if you come up with a priority order like this, then like when you go to the n-arm system, you start with like all the arms with the highest, like whose states are in the highest priority. For example, here is the state 1, so you pull those arms, and then you get to the next priority, and so on until you use like your alpha n budget. So in this case, the next priority is 2. You pull one of them, and you don't have any budget to pull the other one, but you just stop there. Okay, so this is like a reasonable answer B, like in the previous slide. Okay, so yeah, so then like if you look at those kind of policies, this one goes back to all the way to this policy called the Whittle index, which is one of those like index policies, and people prove that it is like indeed asymptotically optimal. But with some assumptions. So here, I'm going to highlight this gap assumption, which is called the global attractor property. Okay, so you will see that like for other policies, they require a similar condition. And then like people can also show that the optimality gap can even be very small if you assume more assumptions, but also like a stronger version of the gap assumption. Okay, so here I'm only listing like just a couple of work here, but Rest Expanded has like a huge like body of work, and just for the flow of the talk, I haven't listed those. Okay, people from MIT have done foundational work here. Okay. Okay, so then if you look at here, then like you can see that everyone like all those like guarantees are subject to this gap or U gap condition. So what this condition is basically if n is large, then you can use the mean field analysis that approximates the stochastic system using a deterministic system that works like a differential equation. In this case, it's just discrete time. Okay, and then like for that like difference equation, you need the system, dynamical system, to have a unique global attractor, and that has to be like a solution, like some like optimal distribution. Okay, so that you need to assume that. Okay, so basically, but I wanted to point out that this is a condition that's a little bit hard to certify. It's kind of hard to verify whether it is satisfied, like if you are given the instance. Okay, you can certify that it's not satisfied, but it's hard to certify it is satisfied. Okay, yeah.
Maybe just a clarification. So why we care about the gap with respect to n? Because n, so n is the number of the states, right?
Oh, sorry, n is the number of arms.
Yes. For example, like if I'm a professor, I
Yeah.
have students.
Yeah.
N is kind of like a fixed number for me. But I'm sorry, I just want to know what's the kind of application that. What I really care is that if I have a small budget, then how much I would do. Or if the budget is really large, then actually I can do individually optimization for each one. So that's independent. What I care is about if I have, for example, if I have a small kind of budget, what is the gap, right?
So yeah, so here the setting, the background is like I mentioned at the beginning, you do have a large scale system. So for example, when you think about the computing system, you have like a large number of servers there, and that is the N here. And in the car routing example, each car, like the number of cars is the number of like arms here. And like even like when N is large, your budget is, although it's proportional to N, it's kind of big, but still like the alpha there is a limiting factor that can like, that is a budget constraint. So you don't really like, you cannot afford to use like, to pull all the arms at the same time.
For example, like here, the C, is the C dependent on alpha or?
Oh yeah, it could depend on alpha and even the state space size. Yeah, but alpha is considered a constant. Yeah, okay. So alpha N is the budget, okay? Okay, so then like I'm going to also show you one example, like to show you what happens if this like a condition is not satisfied, okay? So this is a numerical experiment. The x-axis is the time horizon, and then like the y, or each row here corresponds to like one state, okay? So like this is the previous example where we have 8 states, okay? And then like the intensity here means like how many are, what's the fraction of arms in that state? Like this is a simulation with, I forgot, a lot of arms, okay? And then like you watch like how, so for example, at each time step, if you look at this slice, then you see like the distribution, the state distribution, okay? And then like you can look at how it evolves over time, and you may observe that like here, like it kind of just, it gets stuck in this same distribution maybe after like 200 something time slots, okay? And this distribution, this particular distribution, let me draw it here to make it even a little bit clearer. It's like a distribution that concentrates just on 3 states. Okay, and this is like a bad distribution because remember we only have reward if you go from 7 to 0. If you don't have anything on 7, then you won't be able to have any reward. Okay, so this is a so this shows the case where the distribution is trapped in this like this distribution under the previous policy, and this is like where this distribution itself is another attractor of the problem. Okay, and it doesn't satisfy the gap condition. Okay, yeah.
I think there was a previous question on whether it matters where you start. Is there an interpretation of that here?
So so yeah, I guess, and so for this one, actually, even if you change the start state, it would still like get stuck there. So we tried, and actually here, like if you look at here, it's a uniform. That is like the optimal attractor, but it's unstable for this example. Even if you get there, you could like just get out of it. So for this particular example, it doesn't matter. For some examples, it may matter if you use this policy. Okay. Okay. So so yeah. So this is the example, and so then like in our work, we have like a sequence of work. So first we kind of like remove this gap assumption, but we replace it with another assumption, and that assumption is easier to verify. And the previous example you saw satisfies our assumption, but not like the gap assumption. Okay, but then like later on, we actually like totally removed it. Okay, yeah, there's like this small font like thing here. Everyone assumes a certain aperiodic and unit chain assumption. Okay. Okay, and then like later on, we were able to make the optimality gap even smaller under additional assumptions, but still no gap assumption. Okay, okay, and here I'm going to focus on basically this work. We have a class of policies here that we designed. Okay, okay, so let me get started with our approach. So like I described early on, it has 3 steps. The first step is this decomposition step. If you look at this is the original problem with n arms. And what we are going to do is we are going to relax this condition to a time average, like a time average constraint. Okay? So once we do that, like we can kind of decouple the arms, and basically it becomes like n copies of the same single-armed problem. And the single-arm problem, you just have one arm, you have this reward function. The constraint is like over time, you only pull it for alpha fraction of time, okay? Okay, so this problem now, like you decompose this into n identical copies of this problem. And then like for this problem, next step is to solve it. It's very easily solvable. You notice that like there's no n anywhere, so the complexity doesn't depend on the number of arms. And then like you can, after you solve, this is solvable through a linear program, for example. And then like after you solve it, you get a policy for a single arm. It's like if I look at the state of single arm, what action should I take, okay? And you can prove that this like optimal value is upper bound on the original problem. So if you want to upper bound the optimality gap, you can instead upper bound like this thing with the optimal reward replaced by like this upper bound, okay? Okay, so now like we have done the local solution. Everything is easy so far. And that LP is like that linear program I mentioned is the same thing used by other policy designs too, okay? But the thing we do differently here is we really think about it as a single-armed MDP problem. And we have the optimal solution for that MDP. And then like we are going to use that local solution to construct a global solution.
For example, in your specific example you gave, if alpha is half, effectively sort of, since some single arm, 0, 1, 2, 3.
Yeah, I'm going to show you.
And then, okay.
Yeah, I'm going to show you how it works. And it's like something like what you said, okay? So we have, we call this policy ID policy is one of the policies in the class of policies we designed. So we have this single arm policy, and then like for every arm here, we're going to sample action using this policy. So in this particular example, this is the previous example. Then like we figured out the optimal single arm policy, we sampled those actions, but then like they may not be subject to they may not satisfy the budget constraint, the hard budget constraint, okay? So then what we are going to do is, we want to take the actual actions that are very close to those ideal actions, but we need a way like for this procedure. And the particular way we do this is that we prioritize smaller arm IDs. So here arm IDs are nothing but those numbers you assign to them beforehand, okay? It's kind of arbitrary, but you need to fix them. And once you fix them, you start from the smallest ID, you follow this ideal action, next one also, next one also. Here is all okay, our budget is 4. So then we are here, and now like we have 4 actives, like we hit our budget, then we have to set like the rest to be passive.
So
Okay.
you're choosing IDs rather than doing it random because you need consistent randomization across entire horizon?
Yes, yes. So if you use like a complete random like type breaking, it won't work. We have like numerical experiments showing that. Okay. Yeah, like you said, it's because arms are not consistently like following this ideal policy. Okay. Okay. Yeah. So this is yeah. So it's a very simple policy here. It just works like that. Okay. So now like here, and the guarantee we have is this like 1 over square root of an optimality gap that I showed you before. Okay. So now I want to give you a little bit of intuition on why it works.
R star. So this is a deviation. So if you sort of run the policy individually, and now with this constraint, the implementation for each arm would deviate a little.
Mm-hmm.
And the point is that this deviation is small.
Yes, yes, yes. And you see how exactly it goes here, okay? And it's not a kind of per arm deviation, okay? So, so what happens is like this, okay? So let's think about this example. And our budget is half, so we can pull 4 arms, okay? So now, like, if you think about the first half of the arms, okay? So what do you think will happen to them if we use our policy? Like, we prioritize the smaller IDs. Like, what do you think those arms can do? So
They'll do what's of your individual policies.
yeah, they will just follow the individual policies, exactly, because there's like nothing constraining them here, right? So they will just follow their ideal actions, they follow those policies, and their state distribution would converge to the optimal distribution. And then if they can converge to the optimal distribution, so let's call this the good subset, okay? And then if they converge, then by our design, each arm is only consuming half of the budget on average, okay? So then let's just take that literally. If everyone consumes half, then they together consume 1/4 of n, okay? And then you can look at the next 1/4 fraction of the arms. Now the budget left over is 1/4 of n, and then again nothing is constraining them, so they can follow their ideal actions, and then we expand this good subset to 1 to 3/4 of n. Okay, and then this goes on and on until you can kind of keep expanding it, but due to the randomness in the problem, there's a square root of n fluctuation there, and then that leads to the square root of an optimality gap. Okay, so back to what you commented, the first several arms, they actually don't deviate. Only the bottom arms will deviate from the ideal policies.
Here you're in worst case, so this is one. Yeah.
Yeah. Okay. Okay. So this is basically the
Simulation you see what is n deviation or it's smaller deviation?
It's you mean the gap or
Is the square root of n deviation is the optimal one, or is that sort of
yeah, for the policy it's probably it. Yeah, for our policy it's probably just really square root of n. Yeah. Okay.
So this kind of crucially depends on the number of arms you pull, scaling linearly with the number of total arms.
Yeah, that depends on that.
Number of arms, and it breaks down.
So yeah, so the thing is if your budget is a constant number of arms, then there's not much you can do, and then roughly speaking, your optimality gap would be on the constant order because you're only allowed to pull a constant number of arms. Then your optimization space is small. Okay.
in principle? Here you decomposed into units of arms. N thing, I could say, well, maybe I'll decompose them into log n bit pieces.
Yeah, that's it.
Each problem I'll solve separately.
Yes. Yeah, you can do that. And I think for now, for our particular policy, it kind of works out to be the same optimality order, optimality gap. Yeah. But we do see that phenomenon in another problem where we do need to group them. Yeah. Okay. So yeah, so basically the algorithmic idea here is to just drive a smaller set of arms to optimality first, and then try to expand this set. Okay. So I think maybe I will skip the proof because of time. Okay, and because I do want to talk about the generalization. But it's based on this drift method for the Lyapunov functions, and it's very closely related to this intuition. Okay, so so I'm going to skip those, and our construction of the Lyapunov functions. So sorry, I'm going to just skip them. Okay, I'm happy to talk offline. Okay. So quick summary: we designed this new class of policies. And so it's not a priority or index-based policy, and it does use ARM IDs. So if you don't like the way it makes use of ARM IDs, which seems arbitrary, we do have another design which is not based on ARM IDs, but rather another way of constructing what we call focus set, basically a smaller set where the arms could follow the ideal actions and then try to expand it over time. We explicitly maintains that set in the algorithm. Okay, so then I do want to go to a generalization of this. Okay, so for the rest expanded problem, one limitation is that you only have binary actions for each arm. And you can think that, so there's a quick review here. So the action space is binary. But you can imagine that in many applications, you may want to take multiple actions. When you meet with a student, it could be 1 hour, 2 hours, or 10 minutes, and so on. Okay, so this is the one limitation there, and correspondingly, the constraint is kind of goes with this kind of action space. So weakly coupled MDP is a framework that tries to generalize this. So basically here, the action space could be like an arbitrary finite space, finite set, okay? And then you still have the transition probabilities. Now it depends on action, which is non-binary now. And then you still have the independent transitions, have reward functions, depends on both. So those are similar to before. But here, when you look at the constraints, you could define a cost function that depends on both the state and the action. And you could have multiple types of costs, and you could have a budget for each, okay? So then this is the so-called weakly coupled MDP, and the goal is the same. You find the policy, and it's hard when and it's big, so you want to efficiently compute the policy that has a diminishing optimality gap. Okay.
Because it's the same as before. You've got multiple MDPs now. They have the same their own evolution.
Right.
They're homogeneous.
Yeah, that's the thing I'm getting to next. Yeah. So, but they're homogeneous now. Mm-hmm.
And then they're constrained, or they're coupled together through a constraint like this.
Yeah, through a set of constraints like this for every moment of time. Okay. And we assume there's an action that makes the cost always zero. Otherwise, sometimes it's not satisfiable. Okay. Okay. So this is this setting. And the next limitation I want to bring up, which is even more important in my opinion, is this homogeneous assumption. Okay, so we assume all the arms share the same set of parameters, even here. Okay, but you can imagine in practice, it could be arms are heterogeneous. Okay, so then here we actually kind of we actually consider the fully heterogeneous setting where each arm has its own transition kernel, reward function, and a cost function. Okay, so this is a place where traditional method would really struggle. Mean field-based analysis, would find it very challenging if everything is different from each other. Okay. Okay. So this is this setting, and if you look at previous results for the homogeneous setting of weakly coupled MDPs, we have papers achieving diminishing optimality gap, but with no specific order there. And then there's this typed heterogeneous setting, which says the arms can be divided into a finite number of classes, which doesn't make it very different from the homogeneous setting. Okay, so then those papers assume there's only one constraint, and that's why they can still define certain index policies. Okay, okay, and then what we considered is this fully heterogeneous setting and the general constraints, and we were able to achieve a 1/square root of an optimality gap. Okay, yeah.
Could you clarify again the difference between the typed heterogeneity and a small
Right.
and fully?
Yeah, so the type heterogeneity is you have n arms, they are divided into, let's say, 3 types. And when you increase n, the proportion of each type of arms is fixed. I have 1/3 of type 1, 1/3 of type 2, 1/3 of type 3. Okay, so then it's heterogeneous because you have different types, but if you look at each type, it's still a very large system. So that's why I'm saying it's not too different from the homogeneous setting. Okay.
And the fully heterogeneous, what happens?
So the fully heterogeneous setting, every arm could be different, and when we increase n, as long as we have a condition, as long as that condition is satisfied, then we can just keep adding arms to it. Okay. Okay. Okay, so so then let's see our solution. So we can first go back to this restless bandit setting where we decompose the problem into single-armed MDPs, and as I mentioned, it could be solved through a linear program. This linear program is basically just the state action, long-term state action frequency for this single-armed MDP problem. That's the fraction of time you are in state S using action A. Okay. And then you can solve this LP, you get the optimal solution, which can be converted to this optimal single-armed policy. That's what we actually used, okay? So now like we are going to the wiki-coupled MDP's heterogeneous setting. But we can still first relax the constraints in the same way. So basically, we replace it with the time average constraint, okay? And then, like, although it looks like the arms seem to be still like coupled, but they are not like really coupled, because if you write out the linear program form, it shows it more clearly. Like now we have a set of state action frequency for each arm I. Okay, because each arm is different, okay? And then like this constraint is basically just a linear constraint on those yi of SAs, okay? So then you can solve this LP. Now it depends on n, but it depends like in a like a polynomial way. You have n times s times a like variables, and your constraints are also like polynomial in those parameters, okay? So you can still solve this. And then like you get those optimal solutions. What you can still prove this is like an upper bound for the original problem. And then like what you get is like indifferent optimal single armed policies. Okay, it's just based on this solution. Okay, so yeah, so this is a local step. And then like actually we use the same like a local to global step here. Okay, so what we do is like now we call it ID policy. We need one additional step. Which is like not, it can be done in many ways. It's a pre-processing. We cannot use arbitrary IDs. We need the ID assignment to satisfy certain smoothness kind of condition, but it can always be satisfied. And we have a particular way to do this, okay? And there may be other ways to do it too, okay? But once we fix the IDs, it's very similar to before. Each arm samples the ideal action. So here the actions could be like, I'm just making up numbers here, okay? Representing different actions. And then you try to follow those actions starting from smaller arm IDs. But remember, there's a cost constraint here. And there are multiple cost constraints here. So you start from the smallest arm ID. You keep following this until you hit one of the budget. Okay, then you will stop. As long as one of the budget is going to be violated, you're going to stop, okay? So for this particular example, I think I decided this is the point, like where you hit the budget, then you set the rest of the actions to the non-cost action, which is called the action 0 here, okay? Okay, so yeah, so this is pretty much like a very straightforward generalization of our previous policy, and with this we can prove the optimality gap under the following assumption. So for each like arm, after we figure out the optimal policy, we can look, it becomes a Markov chain if you follow that policy. Then Pi is the transition probability matrix, and we assume it's a aperiodic unit chain, and we need to assume that the mixing time of that arm is upper bounded by a constant. Okay, so this like if we increase the number of arms, we need to make sure this is still satisfied. Okay.
The number of states are, so it's a Markov chain on states.
Yeah, just like we assume they share the same state space.
Yeah, and state space is finite, and so for you to have a uniformly bounded mixing time, in some sense, you want the right sets of maybe the transition kernel with right lower bounds or something like that, right?
Yeah, if it has a lower bound, it can guarantee this. Yeah.
And then sort of course, since it's independent of n, this will always remain true.
You mean if there's a gap, if there's like a lower bound on the transition probabilities? Yes.
And then the only reason sort of the I would change because your linear program would change when you add n, and that's why sort of you want to sort of make sure that that's the case.
Yeah, right. Like it kind of needs to be when you add things. This needs to be still uniformly upper bounded by the same thing. Yeah. So for example, if you are thinking about the typed heterogeneous case, that automatically satisfies this because no matter how many you add, it's like the same upper bound. Okay. So then like we have this result. And something I didn't mention is like if you really look into the constant here, it actually depends on the mixing time. But it depends on the space size only through the mixing time. Okay, so I think in the rest, maybe I still have a couple of minutes, or yeah. So actually, yeah, maybe let me like talk a little bit about the proofs, and both proofs follow the same framework, and so this framework is like based on Lyapunov function analysis, and the basic idea is this: like you want to construct a Lyapunov function. That is first it needs to satisfy certain drift condition. So this drift condition here is basically the expected value of the Lyapunov function in the next time step, given the current state, needs to kind of like shrink. Like it needs to become smaller. Okay, it needs to have a negative drift, and here we allow some like slack there. Okay, another way to write it is like this. Then you can see theta is like smaller than 1, so this is like shrinking, or roughly like a contraction over time. Okay, I guess, yeah, so I didn't put it on this slide. It was on the previous slide, but I'm going to just talk through this. So if you have a drift condition like this, that means you have an upper bound on the expected value of the Lyapunov function in steady state, because you can take expectation on both sides, and then left-hand side becomes 0 because it's stationary, and then like right-hand side is larger than 0, so you move this to the left, and then you have upper bound of the Lyapunov function, okay? And then like the second condition is particular to our problem. So this problem, because we are trying to upper bound this optimality gap, if we can make the Lyapunov function be an upper bound of the optimality gap, then like from the drift condition, we have an upper bound on this term, which then becomes the upper bound on the optimality gap, okay? So then the key thing here is to come up with the right Lyapunov function. Once you identify the right Lyapunov function, then like you have proved the result, okay? So in the previous, yeah, this might be a little bit hard to not have the slide, but maybe, yeah, let me just show you this. So in the homogeneous setting, we already need like a kind of specific construction of the Lyapunov function. This is because, so if you think about the problem in the homogeneous setting, in the restless band setting, a natural Lyapunov function is like you look at the state distribution, the empirical distribution across the arms, and you measure how far away that is from the optimal distribution, okay? The optimal distribution can be obtained through the single-armed problem. So that's the mu star here. But if you do that, if you look at all the arms, this distance may not shrink over time, okay? Because many arms may not be able to follow the ideal actions, so that may not shrink, okay? So what we do there is to come up with this so-called focus set, which is a state, like in the ID policy, it's computable from all the arm states, okay? But this is a subset of arms that can really follow the ideal action. So then like we only measure the distance between the empirical state distribution and this optimal distribution within this set, okay? And then we add on the size of the non-focus set, okay, the size of the arms outside of this DT set, okay? So that's what we did there for the homogeneous setting. Yeah.
Is it okay if I ask a question?
Sure, yeah.
So ST is basically the vector of length n of
Yeah.
each thing,
Right.
DT
Is a subset of arms, and it's
so let's say in that example is top set of arms.
right, and it's stochastic. It's yeah, it's determined by the states.
Okay, and then sort of X is
Yeah, X is the like you count the number of arms in DT that is in each state, and then you divide it by n. Like let's say number of arms in state 0 divided by n, number of arms in state 1 divided by n, and so on.
The mu is somehow sort of the corresponding version of that but under stationary distribution.
Yeah, that's like the stationary distribution of the optimal single-armed problem. And yeah, and shrink it like to match the size. Okay. Okay, so that's for the homogeneous setting. We use this. But if you think about the heterogeneous setting, then this is like no longer doable because you can no longer just count how many arms are in each state. Like arms are different. There's no reason to aggregate them. Okay. but we still want to capture this distance to optimality. And I'm not expecting you to read into this, but I just want to show you the general form of the Lyapunov function. So we kind of, for each arm, we measure the distance to its optimal distribution, and we measure it to see kind of how fast it converges to that distribution. And then we kind of need to project it, convert it into either difference in reward or difference in costs. And and we take max or So basically, we need to project the distance into, translate that into either costs or reward to be able to tell the difference. Okay, so so then this is my last slide, and instead of doing a conclusion, I just want to kind of advocate this approach, and I want to encourage you to find this kind of independent structure in your problem and see and try this local to global approach and see if it works for you. Okay, with that I'll just stop here.